Alright, bring it back, please. Tristan, what is the biggest difference between these three things?
Wait.
Give him a thumb if you agree, a thumb down if you disagree. Tristan, we need it one more time, please. What's the biggest difference between these three things?
The biggest difference is the weight.
Give him a thumb up if you agree, thumb down if you disagree. Absolutely. All three things are moving in the same direction, same speed, but the mass or the weight is the biggest difference. So, here's this guy, Isaac Newton. He sat around many hundreds of years ago and he said, you know what? I understand that weight has a thing to do with it, how fast something is going has something to do with it. He said, what if I was able to define how stuff moves so that we could predict it? Here's an example. If I stand all the way across the room, and put your eye on my wall over there. Okay, that little tiny spot. Could I hit that with a little wad of paper very easily from here?
No.
Okay? Could I hit it very easily if I wanted it to be moving exactly 2.5 miles when it hit the wall? That'd be virtually impossible, right? First of all, you'd have to have the best aim in the world, and you'd have to be able to throw it at just the right speed, right? Let's say that you wanted to send something in orbit around a moon. That's kind of like throwing a little wad of paper just perfectly. What happens if you throw something too hard and you want it to orbit around the moon?
It crashes into the moon.
Could crash into the moon, but what if you're throwing it just to the side? Couldn't it go past the moon? That's not a spaceship I want to get on. Okay? Physics is really, really cool in space because it's all about physics. Unless you know physics, space isn't going to work. So a lot of stuff that we're going to talk about today has to do with that. But you need the rules. So, here's rule number 1. On your paper, I've got part of it filled in for you. All I need you to do is get the rest. So, what it says is, can I just borrow yours for a second? Objects in motion will blank. Object at rest will blank, unless blank. All the parts and pieces are up there. I just need you to add the blank.
I'm not going to make a mistake on this one.
Yeah, I know, right? The thinking will happen. Yes, ma'am.
I'm not going to have a test after our T-SAT, right?
Like ever?
I'm just asking if we're not going to have one after.
Like immediately, like the next week? There's one happening, but it's at the end of the week. I can't remember which day. You're always prepared. Quiz.
Because I don't like quizzes. I'd rather be prepared than say, wait, we got you.
Okay, I need your voices. Actually, no, I don't. That's the next part. Here's my example. If I set this, what is this? I borrowed this from somebody. Face cream on the table. And I leave the room. I come back 10 minutes later and it's on the floor. What can I assume happened while I was gone?
The force.
The force. Okay, Joy, what'd you say? Someone messed with it. What'd you say?
I said earthquake.
Maybe an earthquake. Bottom line is that thing going to move by itself ever?
No.
No, it's going to need some help.
Once you roll it.
What if I go up into space and I throw a baseball? This one's a little bit harder to think about.
It's going to keep moving.
It's going to keep going and going and going and going and going and going forever and ever and ever until what happens to it? Right, so Newton first of all sat down and he said, first of all, Newton never went to space. So this was kind of a stretch for him, but he was right. Objects that are in motion are always going to stay in motion. Just like our planet. It's always going to orbit the sun until something hits it or knocks it out of its orbit or something. The moon is always going to spin around our planet. How about this? If you go out into the parking lot, drop my parking brake and start rolling my car. Please don't. What's going to... So according to Newton, it should keep going forever and ever and ever, right?
So
Why doesn't it?
and that's something.
It's going to crash into something.
Oh, not gravity. What is it called when I rub my hands together and it starts to
Friction.
Friction. So friction can slow stuff down. That's usually the one that we're talking about. Let's get with it.
Is that why, because, it's just a question, is that why they made that statement talking about an apple doesn't fall too far from the tree?
Oh, no, that's like genetics. So like if an apple falls from the tree, it has seeds in it, you're a lot like your parents. Your parents being the tree, you being the apple.
Okay.
You're never too much different than your parents. That's the thing. Okay, so we're going to skip the your example part. I need you to go down to number 2. Sorry, just we got to keep moving. Is it important?
No, not really.
Okay, number 2. Newton then said, okay, things stay in motion if they're in motion. Things are going to stay put if they're set down. There's more. An object's force depends on how heavy it is and how much its speed changes. on a couple. Please put your pencils down and you are set to go, please. Alright, all the pencils are down? Almost? Alright, here's my example. Oh, come on. If I were to walk up and just haul off and kick your desk as hard as I could, it would rattle and shake around. Okay? What if I dipped my foot in concrete and made it like 10 times heavier, and then came in and swung as hard as I could and then kicked your desk? The desk would probably like kick over, and if I was really strong, I'd probably like send it flying, right? In either case, my foot is moving only so fast in both cases, right? Okay? And object force depends on how heavy it is. That was from our warm-up question. Also, how much the speed's changing. What if I take a tennis ball and I throw it and I hit it against you? Not a big deal, right? Right.
Yes.
Okay. Then I take like a pool ball and I throw it and I hit it at you at the same speed. Okay? If you were to put those on slow-mo, you know, like you guys watch Mythbusters, right?
Yeah.
You know when they show everything like on slow-mo and it's really cool looking? When the tennis ball hits you, you know how tennis balls are squishy, yes? It kind of like squishes into you and it makes it take longer to slow down. But a pool ball, is a pool ball squishy? Obviously not. When a pool ball hits you, it just stops, right? So a pool ball hurts more, it applies more force because it's heavier, and because it slows down way faster. The second part is kind of hard to get your brain around until you have more examples, and so we'll do that. But then Newton said there's more. There's a third one. Oh, sorry, there's 2 bullet points I need to have. So more mass means more force, or the heavier it is. Also like this. It kind of works the other way too. Let's say you've got a parked car, and you want to get it going really, really fast. Do you want your car to be really heavy or really light?
Heavy.
You want to get it going fast, and you want your car to be heavy? You're just playing. You want it to be light. Jet planes are not light, so does it take a long time to get them rolling fast? Obviously, yeah. So the more force you add, the more it's going to get going faster. The heavier it is, the more force it's going to take. Then Newton's third law. I know you're still going, but get third in there. This one's probably the most challenging for me to get my brain around. For every action, there's an equal and opposite.
Reaction.
Yeah, but I've worded it differently. So Joyce, you've heard this before. I'm sure others of us have also. For every force in one direction, there's an equal and opposite force in the opposite direction. I bet at first, when I first heard this one, I was like, that can't be true. That doesn't sound right at all. I'm going to show you. You do this all the time. Sorry?
I said a sport or
Any. You swim, right?
yeah.
Swimming. I've got a swimming example coming.
Awesome.
Joyce, you hate swimming? You've got long arms. I mean,
Seriously, Joyce, you're the fastest. Going 30 miles per hour.
I don't know about 30 miles an hour. It's like
Okay, let's say
motorboat.
100.
Okay, almost got everybody. Just a few more seconds. Anthony, you ready? You're done with your notes. Good, right? Okay, so here's your example. Pencils down. I want you to put your eyes up here. Unless, if I'm going to want to go from here to there, unless something pushes me there, am I ever going to get there? No, because of what? Am I at rest or in motion right now?
Rest.
Rest. So the only way to get me from A to B over there is if what happens?
You get emotion.
Something forces me, right? Okay, so the question is what? Everybody knows how to walk in this room, so when you walk, this is where it starts to get a little crazy in the brain. Am I pushing on the floor as I walk? Okay? The only way for me to get going that direction is if the floor pushes back. Here's another example. Why am I not falling over?
Because the wall is pushing the wall.
So the wall is pushing me up, so as I push against the wall,
It's pushing you back.
yeah, this is probably the easiest one to see. How about this one? Why am I not shooting straight to the center of the earth right now?
Because the floor is pushing you back.
Because gravity's pulling me down, so why doesn't it pull me straight to the center of the earth?
Because
that's
the floor is
The floor is pushing me right back. So as I push down with gravity with my weight, the floor has to push me right back in the exact same opposite force.
But that's why you're not going
So it's hard to get your brain around, isn't it? We're going to do a bunch of examples. Yeah.